Hello, and welcome to today's session. This is part of the series of sessions leading up to the Ascend event in November. Please check out ascend.events for more information on all of the activities. We ask everyone to remain on mute while in this main room to eliminate background noise. Your mute button is in the lower left corner. Now, we're happy to welcome Jessica Clark and the team at the Association for Spaceflight Professionals.
All right. Can everyone see the slides okay? Can everyone hear me? All right, great. Well, welcome everybody. Welcome. Thank you for joining us this morning, wherever you are in the world. So we are here today, have a very exciting topic for you all today. It's the developing of the next generation of commercial astronaut stories in space medicine, technology development, and building a new space community. So it's very exciting here for us at ASP to talk to you guys. I'm going to introduce myself here. We are part of ASP, and my name is Jessica Clark. I will be your moderator for today. I am the Education Outreach Officer with the Association of Spaceflight Professionals. A little bit about my background. I am a graduate researcher at Arizona State University. My focus is on human factors in extreme environments. And I have certificates in performance physiology, psychology, wilderness medicine, and Antarctic and marine sciences. So before I introduce our speakers today, I'll tell a little bit about ASP. So ASP, we are a nonprofit organization, and our members stem from students to seasoned professionals from various backgrounds, and we all focus on the space industry. So whether it's space law, engineering, medicine, or entrepreneurship, our membership focuses on catering to the needs of our membership. So our first speaker today is going to be our President and CEO, Dr. Michael Gallagher. He is a fantastic person. He will be talking about the solving medical problems in the space and rural environments. So about Michael, he is a assistant clinical professor at the University of Alberta. He graduated from the International Space University in Space Studies, and he also completed Principles of Aviation Space Medicine short course in the University of Texas in 2015. He holds a certificate in advanced scuba diving, and he is president of Association of Spaceflight Professionals, or ASP for short, and he's the president of Aerospace Medicine Association Corporate Forum. Our next speaker is Dr. Shonda Pandia, and she is here with us, and she will discuss the experiences and spaceflight analogs. Very exciting. Dr. Shonda Pandia, she is a scientist astronaut candidate with Project Possum, a physician, aquanaut, a pilot in training, skydiver, and she is an advanced scuba diver. She is a VP of Immersive Medicine at LOX Technologies and a fellow of the Explorers Club. She holds degrees in neuroscience from the University of Alberta, a Master's of Science in Space Studies from the International Space University, a degree in entrepreneurship from Singularity University, and she's also completing her fellowship in wilderness medicine. So this is Dr. Shonda Pandia. Our next speaker today will be Brett Bennett, and he is our business development officer. He will be discussing risk management and flight assurance with small sat missions. Brett, he is an entrepreneur, a a human performance researcher and focusing on bio astronautics and expeditional leadership. His degree is in neuroscience, genetics, and he's worked on development of training realms and EEG-based technologies. So these are our wonderful speakers today, and we all come together for our mission. So our mission is to develop the next generation of commercial astronauts through creating networking, education, and research and mission opportunities for space professionals. So we're here to create awareness and have you be interested in our discussion topics today to help build the next generation. So what ASP is, we bridge gaps, we solve problems, we stimulate conversations, and test and create technologies. And we are creating a platform, if you would say, or launch pad for individuals in industry or coming into industry and who are already in industry. So we have several initiatives stemming from educational content and technological development. We do educational series with the Space 101, and we have monthly talks about different interdisciplinary approaches that are going on in space. And so we have nutrition in the space realm. We have small sat. We have space law. We talk about different entities that are important in space. We've also, our scope of success, we've also been completed a literature review for space flight medical guidelines and professional development. We've also are collaborating with different universities in the United States, Canada, and around the world. We are focusing on developing technologies in a free-flowing locker, auto transfusion, and LBMP sleeping bags. And we also have collaborations with different analog opportunities like with NASTAR and Project Possum. So with that, I'm going to bring it over to Brett, and he's going to discuss a little bit more about what else we do here at ASP.
Yeah, thank you so much, Jessica. And thanks again to everybody tuning in globally. I think today's topic is especially relevant for a burgeoning space industry, and we'd like to showcase some of our offerings as we continue to develop and work towards our mission. Jessica, if you could advance the slide, please. Actually, we'll go back to, please, Jessica. Perfect. So let's see. NASA in 2017 actually started their plan to transition in a stepwise approach from the current regime that they're using in low Earth orbit. It relies heavily on the International Space Station as a governmental platform and the associated NASA sponsorship. It was at that time that they started this transition in earnest to change to a regime where NASA would be one of many customers within a low Earth orbit, non-governmental human spaceflight enterprise. And they've associated with that transition, they've performed several studies to really drill into what they can forecast for both governmental and private demand for commercial human spaceflight. And that's really what this infographic illustrates here. It's broken into 5 key parts. The first is a strategic plan that NASA has outlined for its commercial partners. That's really based on 4 main pillars. And those can be summarized by number one, achieving a continuous human presence within low Earth orbit. Number two, fostering a regulatory environment that allows for commercial activity to thrive. And then that one is closely followed by something that's near and dear to ASP as an organization, which is human spaceflight research for long duration human spaceflight. And they round out this set of key initiatives with their expanse into commercial opportunity as afforded by international partnerships. Now, the initiatives and categories of demand that directly support that overall strategic plan are further subdivided into 4 key areas. One is human research, another is physical and biological research, ongoing atmospheric and solar system science, and lastly would be tech demonstration. NASA has been able to quantify how much they would be requiring these services and how it can be directly supported by a brand new generation of private entities that are supplying qualified crew for these types of orbital mission architectures. So with that in mind, ASP has decided to pursue the development of that next generation. Jessica's already alluded to some of ASP's major successes in these areas. Jessica, if you could advance the slide. This is the first of several. Jessica mentioned that our literature review, as emphasized by some of our team members with medical expertise, have been able to pursue a literature review that's produced a first draft for medical guidelines for commercial human spaceflight. This was actually a review that was submitted to last year's International Astronautical Congress in DC. It was a sound success, and it was divided into 9 key areas, 9 or 10 key areas that have the potential to directly affect the establishment of a set of medical guidelines. This is a key step for establishing and then dynamically revising medical standards and certifications as they apply to commercial crew and spaceflight participants. Go ahead and advance the slide. Thank you, Jessica, I appreciate it. So ASP's tech development is really aimed at advancing technology readiness levels for a variety of projects. This type of initiative allows student teams as well as professionals that are already within industry to participate in the advancement of new spaceflight hardware and software. What we see here is a platform for a lower body negative pressure sleeping bag, or just LBNP in general. This is a crucial technique for dealing with microgravity, especially on longer duration missions. When astronauts become weightless in space, fluid in the body shifts towards the head. And when they return to Earth, the body isn't really accustomed to gravity, at least during the transitionary period. And so more fluids actually will pool in the legs. Because this can cause astronauts to be pretty nauseous and dizzy, or even cause fainting. A lower body negative pressure, or LBNP device, is designed to counteract this. And on the left, we see the CSA, the Canadian Space Agency's LBNP device. And on the right, we have the Russian Cheetah suit, which is aimed with the same outcomes. Go ahead and advance there, Jessica. So this is actually a design that was originally conceptualized by one of the University of Toronto's engineering design teams. They're actually trying to create LBNP sleeping bag prototype with one inflatable and one non-inflatable layer, as illustrated here. By doing this, they tried to make a structure that can be rigid and round when inflated, and also easily collapsible and storable at the same time. That's necessary for when it is not in use. Go ahead and, yeah, thank you, Jessica. This is a photo of that development, essentially the advancement of the prototype, and this is what they were able to accomplish using materials including nylon and silicone. In this particular project, ASP and the student team is aiming to get a fully functional prototype assembled and then built. So an entirely separate, but I would say equally applicable set of technologies is the auto transfusion device that is, I would say, stylized here. In the case where a physician is confronted with a bleeding situation, some sort of a traumatic injury for a patient, and they at the same time do not have access to either matching blood of the correct blood type or insufficient amounts of that blood, they need to be able to transfuse the patient's own blood to address that injury and treatment. This is especially true for any sort of on-orbit accident where mass and gravitational considerations are obviously at the forefront of any sort of medical care. And so what does it look like to actually have an auto transfusion device that works in that environment? This is also something that we are actively pursuing and developing. And I will add just a few other notes to this particular slide, since it does have the capacity to really change how potential either surgical procedures or other injury procedures are actually performed in the spaceflight environment. When you see auto transfusion device being used today on Earth, you'll see them in operating rooms, and they're usually big, bulky, and require a technician. And if they could become smaller and simpler, they would be useful not just in rural hospitals, but also on longer duration spaceflight missions. So in our partnership with the University of Toronto, an engineering student group is tasked to build a miniaturized and simplified component of an auto transfusion device that could be flown in parabolic flight as a test bed. They managed to build a prototype in the centrifuge component, and they've even been able to separate red blood cells with that device. This is, so go ahead and advance if you could there. Yeah, thank you, Jessica. This is an example of our ongoing educational initiative for our member base. At ASP, we've established the Space 101 lecture series. This is aimed at a wide spectrum of audience members, everywhere from active astronauts all the way down to university or even high school students. What we see here was a presentation authored by one of our members, Captain Alex McHale, on crew dynamics, mission planning considerations, and the after-action review. So I'd like to turn the microphone over to Michael Gallagher. He is our president and CEO at ASP. as we've already heard, and he would like to expand on what we're offering for educational content and describe his experiences in solving medical problems in rural and space environments. Go ahead, Michael.
Great. Thanks so much, Brett. And good morning to everybody, and or good afternoon, depending upon where you're in the world you are, maybe even good evening. So yes, I'd like to take you through a little bit about how we approach medical problems in space and rural environments as physicians. So Jessica's given a great introduction. I'm a family doctor. I work mostly at the Canadian Forces Base in Edmonton, but also managed to get connected to space in 2010. And would like to kind of give you a bit of an idea about, you know, a lot of you are probably in very different fields. It could be business, it could be engineering, perhaps law, politics, that sort of thing. But it's also really important to kind of understand the basics of one another's kind of domains of knowledge and everything, so that we can learn to kind of work together in this environment that really demands a multidisciplinary approach. So I'll have you do next slide, please, Jessica. So what I'd like to do is I'd like to take you through some of the similarities between space medicine and rural medicine, and also a bit about spaceflight's effects on the human body, so you really understand at a very basic level what we're trying to solve to be able to make space safer and to be able to go farther in terms of space exploration. The other thing I'd like to do is give you a sense of just how complicated the human body is, and taking that into account, kind of how medicine has attempted to evolve towards you know, and refined itself towards caring for sick patients. So we'll have you do next slide, Jessica. Okay, perfect. So, so this is what happened in 2010. I was very fortunate to be able to do an elective at NASA's Kennedy Space Center in 2010. Was able to be part of medical triage forces for Space Shuttle Discovery's launch and landing. And kind of through that, I wanted to see how I could continue to be involved in space. Now, I did do a few things like the International Space University Space Studies program, and then also the University of Texas Principles of Aviation Space Medicine short course, where we get lots of lectures by NASA scientists and flight surgeons to kind of give us a better understanding of space medicine. But really wanted to kind of figure out, how do I continue to be involved, and how do I expand that ability for more people to be involved in space? So I took over what is now Association of Spaceflight Professionals, and we're trying to figure out, you know, how do we continue to expand this opportunity for people so that they can make meaningful contributions to space, and then by doing so, we as in humanity advance ourselves towards achieving more in space exploration. So we'll do next slide. But this is my day job. I'm from Canada. I work in rural Alberta. I also have gotten some qualifications through the Canadian Forces in dive medicine. And so what's been really neat over time is to kind of just see, okay, you know, what are some of the similarities between rural medicine and military medicine and dive medicine and space medicine. So I'll have you do next slide, Jessica. Thanks. So yeah, I live here in Canada. It's an extreme environment for much of the year. It gets really, really cold. And, you know, in fact, it's so cold that pretty much 90% of the population is very, very close to the US border. We kind of just like huddle along the border for warmth, pretty much. But what that means is that we still have a number of people who live in the northern parts of our country in very small places that we have to figure out, okay, how do we take good care of our citizens who are living in these places? How do we set them up with the right medical care so they're getting solid world-class health care? And how do we make sure that if we can't take care of them where we are or where they are in those small towns, that we can get them to a place where they can get solid medical care? So we'll have you do next slide. And in fact, this is kind of similar to the International Space Station. Really, when you look at ISS, you have about the same medical capability on ISS as you might have at a base camp at Mount Everest. And the other thing that's really important to understand is that if an astronaut gets really sick, they have to be evacuated back to Earth. And sometimes that can take about 24 hours. So like in rural medicine, when you're looking at space medicine and you're dealing with a sick astronaut, or if I'm dealing with a sick patient in a small rural hospital, or if Shonda's doing the same thing because she does a lot of rural locums as well, we have to ask three questions. what do we do to help this patient with what we have available to us? How do we get a patient out of that environment if we aren't able to help them there, and to an environment where we can help them? In many cases, a larger hospital with more specialists and more equipment available. And then the third thing that we have to look at is saying, okay, you know, because no doctor knows everything, who do we talk with who might have a bit more knowledge in a certain medical area than we do? And how do we use their knowledge to help us care for a patient? So we'll have you do next slide, Jessica. So again, I'm just going to review some of the similarities between rural and space medicine. And for those who are in engineering or in business or in politics, I mean, these are the key things that just need to be solved for us to deliver better rural medical care to patients, and also to be able to push a bit farther in space medicine. We have to deal with long transport times. So several hours often to get a patient from the place that they are in a rural community or in space to a larger place. There's limited equipment. A few small towns maybe have CT scanners, but almost none of them have MRIs, and certainly on the space station, you're not going to be able to have a CT scanner or an MRI at this point in time. There are few to no specialists available. There are limited hospital staff. In a rural hospital, you might have a nurse on call at night with you, maybe two. And then if you're in space, you might have your crewmates who have a bit of basic medical training. And also, it can be really, really, really cold outside. So we'll have you go to the next slide. All right, so the one thing that was interesting was I was kind of trying to figure out, okay, how do I, as a physician, not knowing a lot in engineering, become more involved in space and technology development and being able to solve certain problems in space? And so International Space University was a great place to meet all sorts of people from various different disciplines. This fellow in the center's name is Magne Johansson, and he said something really interesting to me. He said, you know, Michael, I'm in the engineering field, and engineers are amazing at making it all sorts of wonderful technologies. But what we sometimes have some difficulty with is actually, you know, taking the technology we've made and applying it to solve a real world problem. I'll have you do next slide, Jessica. Thanks. So what he said is, Michael, as a doctor, you're what's called a problem holder. You might not be able to design technology all that well. You probably forgot a lot of your integral calculus that you learned way, way back. But what you can do is you can say to an engineer, hey, I think your device could be really useful to help solve this particular problem in medicine. So we'll have you do the next slide. And on this slide, I'm going to show you as a brief overview the things that we need to address in space to be able to make it safer for people and to be able to go farther in space. So really, if I had to sum up what happens when you're in weightlessness and in an area of a lot of radiation is space kind of makes you age really quickly. Your bones start to get a lot thinner, your muscles start to kind of waste away a little bit. You get this fluid shift to the head that Brett had mentioned. And so sometimes you can do certain things to counteract that, like the lower body negative pressure device. You also have a lot of trouble figuring out which way is up because you don't have a lot of gravity. So your inner ear sensors kind of get, what are called your otoliths kind of get all messed up a little bit. So it takes a while to regain your balance when you come back to Earth. The other thing is the kidneys don't filter quite as well. So you're also getting a lot of that calcium from the bone that's being lost that can then kind of actually create some stones in the kidney. So you have a higher chance of kidney stones. So those, among a few other things, are key things that we have to solve in space. And they primarily relate to astronauts being weightless, and some of it also relates to space radiation. So we'll have you go to the next slide. So here's a thought, and I want to just also give you a context of how complicated the human body is and what makes it really difficult and sometimes kind of imperfect in terms of how we figure out how we approach helping patients. So if we thought of the human body as a machine, what would we see? So we'll have you go next slide. So let's kind of just take down the skin here. And so what you see is you say, well, maybe that's not too complicated. You have lungs that kind of take in air and breathe out. You have a stomach that kind of mashes up food. You have intestines that kind of just take the food through them and then kind of just absorb them into the body. But then we go a little layer deeper. We'll do next slide. And then we see the heart. And you say, well, it's a little more complicated, but really it's kind of just a pump. You know, you get blood that comes in through these big things called the superior vena cava, and then you get blood going out through the aorta. And so you just, you've got and a few of these other pipes here. So you think, okay, well, it's kind of plumbing, but let's go an order of magnitude deeper. We'll go to the next slide. Perfect. So what you see is now you start to see a lot more complexity going on. And in fact, if you took you look at the heart, and it's made up of millions and billions of these things called cells. And so if you take, even a bit of the heart muscle out and put it in a petri dish, you'll actually see these heart cells beating in synchrony. And inside these heart cells, you see all of these different little things called myofibrils that are kind of contracting the heart cells. And then if you look even deeper, and I'll have you go to the next slide, we get to an even more complicated situation. You have got all of these different proteins and enzymes whizzing around inside the cell, doing all these sorts of things, going into this bigger thing called the nucleus here, reading instructions from DNA, whizzing around outside. And what I've shown you here isn't the totality of everything that's going on. In fact, this is actually a pathway, one pathway that's activated when something's going wrong in the heart. And we'll even take just one of these structures called calcineurin. So we'll go to the next slide here. And even that, that is still a very complicated structure. And it folds and it bends and it binds to different things. And it just does all sorts of really complicated things. And so that's the same sort of structure as a lot of these different things in a heart cell. So you kind of think, well, geez, how do we even possibly approach helping a sick patient? And in fact, it's really kind of, medicine has really evolved from a lot of ancient kind of different practices that have only recently kind of been informed and refined and by science and randomized controlled trials. So if I had to summarize it, medicine really is a trade craft that's heavily informed by science. And there's still a lot that we have to understand about how we help patients and do things well. So I'm going to go to the next slide, and I'm not sure if we can do participation as much here, and I know I'm running out of time a little bit. So I'm going to just give you a few of the answers about where do doctors get most of our information about a patient's illness. And so we'll kind of go to the next slide. And so what actually, some people might think, well, it's MRIs, it's CT scans, it's labs, it's all that, but actually it's not. We actually get most of our information from talking to a patient and from doing physical exams. Once we start to get to lab tests and MRIs and everything, that tends to confirm what we're thinking and only contributes to about 20% of kind of what we're able to figure out about what's going on for a patient. An exception to this is ultrasound, and we're starting to say as physicians that this is kind of an extension of our physical exam. So that's an example for engineers out there of a piece of technology that's really making a lot of headway in medicine and is certainly used in space quite a bit. So we'll go to the next slide. The other thing I'll ask is what health interventions do you think save the most lives? And so a lot of folks might think, well, it would be going in and having a surgery, or it might be your friendly doctor in the emergency department who is saving your life. But actually, if you look at it, people might even say, oh, it's me, it's a family doctor, your regular family doctor. But actually, it's your public health officer. It's preventing that beautifully complicated body from getting hurt in the first place. So seatbelts, speed limits, sanitation. Sanitation's been a huge factor in terms of increasing our lifespan. And that's a similar sort of thing when we look at also how do you care for your body well, giving it the best building blocks that you can get: healthy diet, moderate exercise, quality social interactions. And then if we kind of go to the next points here, you then start to see, Sean and I there with preventative medicine, family doctor visits. And then if we go to the next 3 points there, then you see emergency medicine, surgery, and intensive care. And so those are, so that when you're looking at designing a spacecraft, probably the best thing you can do for your astronaut is build a fantastic spaceship, make sure they've got good food, they have an ability to exercise, and they've got a good crew around them that can support them through a difficult mission. So we'll go to the next slide here. So Brett's already given you a bit of an example of some of the things we're doing. Now you might ask why we're doing what we're doing. And so that really what we're trying to do is we're trying to be able to build different experiments and technologies and build people's capabilities to be able to test equipment in various different space analog environments like microgravity flights and space analog missions, but we're also, there's a bit of a deeper level to this. And it's something to be said for, in our very difficult polarized environment, we need more situations where people can come together to work in difficult problems and in difficult environments to be able to achieve great things together. And in environments where you aren't just together and drawing from people from different backgrounds because it's nice, but because the environment demands it. And this is an example of something called the Apollo-Soyuz test project, where at the height of the Cold War, US and Russian astronauts got together and managed, despite their conflict, to do something amazing in space. So I'll just go to the last slide here, and I'd like to leave you with this beautiful photo of a hydrazine plume, the shuttle exhaust plume being lit up by a sunrise during my time in 2010 with Space Shuttle Discovery. I do believe that a world with more astronauts is a better world. And I think that now more than ever is our time to craft a better world with everything going on. We have to do this now, and we are going to be right there with you, helping you do that. Thank you very much.
All right, thank you, Michael. Stimulating as always. All right, our next speaker is Dr. Shonda Pandia. She's going to be discussing the experiences and spaceflight analogs. And I will share my screen with you, Shonda.
Just a note, Dr. Shonda, if you can unmute yourself.
Yes, perfect. 9 months into 2020, I still have not figured out the mute button. So sorry. Can do space things, can save lives, cannot unmute. So thank you so much for that incredible presentation. As always, Mike, you are a tough act to follow, but for once it was not me giving the space medicine talk. So always fun to sit back and enjoy. So everyone, welcome. Thank you so much for coming. When you're putting together a panel with great ambitions like this, you always secretly worry that no one will show up. So to see 40 plus people here today is really validates the work we're doing. Thank you so much to my teammates, Brett and Jessica as well. You guys are always wonderful in organization. So I think we're running a little bit behind schedule. So instead of 15 minutes, I will try to condense 40 slides down to 10 minutes, but I have a lot of caffeine in my system this morning. So I think we'll be able to do it. So you guys heard, my name is Dr. Shonda Pandia. I am the life sciences team lead for the Association of Spaceflight Professionals. I'm a physician, aquanaut scientist, astronaut candidate, pilot and training, skydiver, martial artist, speaker, and VP of Immersive Medicine with electronic technologies. So we don't need to go through all of it because you've heard who I am already. Here is a picture is worth 1,000 words slide, rather than just kind of telling you about my credentials. But honestly, that's what we're going to take the next 10 minutes to talk about. So to remind ourselves, the mandate of the Association of Spaceflight Professionals, ASP, you've heard a lot of it, but to summarize, is to develop networking, funding, research, technology development, and mission opportunities for the next generation of not just commercial astronauts, but spaceflight professionals. So in my time here today, I'm going to be specifically talking about analog environments and where that ties in to our future roadmap and why we care about them. So by the end of the session, my hope is that you'll have a sense of what analog environments are, why they're valuable for human spaceflight research, and how they tie into our bigger vision of commercial spaceflight and opportunities for spaceflight professionals going forward. So let's get to it. Let's start with a question. What is an analog environment anyways? Well, if you've ever trained in med school or grad school, the typical thing is to flip the question on its head and ask, well, what do you think an analog environment is? So I'll give you a bit of a hint. What do all of these environments, whether you're looking at teamwork in caves, this is a shot from the ESA Caves project, to microgravity and parabolic flight. There's Richard Branson, to remote deployment in the Arctic or Antarctica, or a mission, a scientific mission at the Aquarius Reef Base where NASA runs its NEMO, or NASA Extreme Environment Mission Operations. What do they all have in common? Well, I won't keep you in suspense, but these are all examples of an analog environment. And so an analog environment is one that replicates some aspect of the spaceflight environment, whether that's microgravity, whether that's isolation and confinement, whether that's being resource limited. So why do we care? Well, Mike did a great job of explaining a lot of the risks of spaceflight, but to quickly recap, spaceflight, imagine you wake up on Mars. It's going to be a little bit different from waking up on Earth. Your priorities and your resources are a little bit different. If you think back to the amount of resources that went into the Apollo era moon landing, it was a heck of a lot, and it was super, super. And to recap Mike's talk, space is trying to kill you. So why do we care about analog? Space is hard, space is expensive, and space is trying to kill us. Therefore, it makes sense to rehearse every possible contingency on Earth and know all the risks, all your protocols, test your technologies before you ever get to that high risk, high expense environment. And so for the next part of the talk, I'm going to tell you about my experiences in various analog environments. So here's a shot of, I think it's Chris Hadfield, in the NASA neutral buoyancy facility where they have a full-on mock-up of the ISS and they do EVA work in spacewalk simulations. So not as cool as Chris Hadfield, but hopefully you'll get something out of my experience. So we're going to talk about 4 different types of analog environments in the next couple of minutes and what we've learned from them. So the first type of analog that I want to tell you about is one we've alluded to already, and that's micro and partial gravity environments. And so Mike has already told you about what space does to our bones, our muscles, our fluid shift, our cardiovascular system, everything else. It's a lot. So we have decades of human spaceflight research from the ISS, but when we talk about getting something space ready, we talk about TRL because in space, we love our acronyms. So TRL stands for Technology Readiness Level. So you can't just randomly draw a technology concept on a napkin in a bar one night and then say, hey, I've got a solution for space. You have to get it space ready. And to do that, you go from TRL1, that concept phase, to getting it space flight ready, all the way to TRL9. So this is an example of an IVA or intervehicular activity spacesuit that we have tested in progressive campaigns since 2015 to get it increasingly space flight ready. And this is done through one of our sister organizations, POSSUM, also known as the International Institute of Astronautical Sciences. So we were the first crew in this particular flight to test the commercial spacesuit in microgravity. We've gone on to do scientific payload demonstrations and technology tests. The other challenge with gravity is we know from decades of spaceflight what microgravity does, and every single one of us, unless you're tuning in from the ISS, in which case, hi, every one of us on this webinar has the luxury of being in 1G. But what happens when you go to partial gravity, like 1/6 gravity on the moon, 1/3 gravity on Mars? Well, there's a lot to be figured out. So you may as well test as much as you can on Earth. And so here's a shot from the Canadian Space Agency last year, where again, with our sister organization, POSSUM, we tested the Final Frontier Design EVA, or extravehicular activity suit. And here I am simulating work on an ISS panel. And the way we do that, and the way we offload gravity without ever leaving the confines of Earth or even the ground here, is through a gravity offset system. So you can see that I'm attached to a harness. And that I'm offloading my entirety of weight so I can simulate what microgravity would be like in that spacesuit. So there's one of our first analog test beds. Talk a little bit about water analogs now. So there's underwater analogs and above water analogs. So here's another example of IVA spacesuit testing in an Orion capsule mock-up. You can see there behind me. So in this case, it was an egress scenario, and we were testing how the IVA spacesuit would react when you have to perform an emergency egress from the capsule. And in this case, I had to egress from the craft, seal my suit, deploy my portable flotation devices, swim all over to the raft you see behind me, and then declare myself home free. And the reason we test is because I learned the hard way, it's super important to pull all the seals in their entirety on the IVA suit, because it's super hard to climb up a rope ladder in a spacesuit full of water. Let's talk a little bit about underwater analogs now. So last year, I was lucky enough to attain my aquanaut designation through the Neptune mission. This was a citizen science-driven mission. Neptune is another acronym. You'll see a theme here. Stands for Nautical Experiments in Physiology, Technology, and underwater exploration. And we performed this in the Florida Keys at the Jules Undersea Lodge. We performed scientific experiments related to physiology, cognition, and psychology, as well as technology demonstrations. So you can see here, this is my other hat with Luxonic Technologies. We are deploying one of what we believe is the first demonstration of a virtual radiological reading room underwater. And in this scenario, I was connected with the head of radiology in Saskatoon, Canada, and we went over a trauma patient imaging together. The last underwater analog I want to tell you about is the Aquarius Reef Base, which I told you about a little bit earlier in the introduction. And so this is yet another underwater analog where NASA performs crew dynamics studies, scientific missions, technology deployments. And I was lucky enough to attain my dive medical technician designation there last year. And the value of this particular analog is it's actually much deeper than the Jules Undersea Lodge. So Jules is 20 feet underwater. Aquarius is 50 feet underwater. And without going into all of the physiology of why that's important is when you're in depth, you actually have to decompress safely. You can't just shoot up to the surface. You have to let all of those dissolved gases in your body seep out slowly so you avoid the risk of decompression sickness or a gas bubble lodging somewhere bad like your brain. So you're actually closer physically to a hospital at Aquarius than you are on the ISS. But to safely decompress, you need to wait 15 hours and 47 minutes to avoid a decompression injury. Whereas the second you hit the evacuation button on ISS, you can get to Kazakhstan in 3.5 hours. So it is a very good analog of what remote support and remote care and stabilization will look like. All right, so I suspect I'm running out of time here, so we'll zoom along. So the last environment I want to talk to you about is isolated, second last, is isolated and confined environments. So this one kind of speaks for itself. The more remote we are, the more independent we need to be. And so at the Mars Desert Research Station, I've been lucky enough to do 2 tours there now as commander and as crew health and safety officer. You know, you learn about living in a tin can, real life on fake Mars, and learning to be self-sufficient, learning to don a spacesuit every time you go out on an EVA, to focus on crew dynamics, as well as living independently. Plus, you get to see some pretty cool landscapes. The last thing I want to talk about is resource-limited environments. So you can actually create an analog in your backyard if you wanted to. And so these next slides are from one of the courses I run through POSSUM, the Operational Space Medicine course, where we essentially teach you to be a medical MacGyver with very limited resources at your disposal, and using principles of wilderness medicine, learn to assess, triage, and treat basic medical conditions having no medical background, and how you would apply those to the spaceflight environment. This final shot is from Cinder Lake, where we, again, through POSSUM, completed the planetary geology course, and basically, again, in a simulated lunar environment, tested geological tools that might be used on a lunar geology survey. Okay, so lessons learned from my personal experience. Teamwork is key. You have to plan for downtime. Plan for best and worst case scenarios and everything in between, and the most likely scenarios. Have a plan, a backup plan, and a backup plan. So how does this translate to ASP going forward, and why do we care? Space is hard, space is expensive, and space is trying to kill you. Analog environments allow us to identify and mitigate risks, test new technologies and protocols, build and work on those team dynamics, and practice good expeditionary behavior, as well as practice our contingencies, and I hope to have convinced you they're super fun. So let's come back to the ASP mandate. This is a shot from a 700-foot drone outside the MDRS, thought I would include it there. So the ASP mandate, we want to develop networking, funding, research, technology development, and mission opportunities for the next generation of spaceflight professionals and commercial astronauts. So translating this into practical opportunities going forward as part of our roadmap, we see payload and technology development opportunities, protocol development and testing opportunities, analog missions with the opportunities to develop our own crews and crew dynamics, flight opportunities in parabolic flight. And in fact, we've already sponsored one student team for parabolic flight earlier this year, pandemic notwithstanding, and the crew dynamics I already alluded to. So I think I am at time. Hopefully that gives you a good sense of why these analogs are important and how they fit into our roadmap. And without further ado, I will turn it back over to Jessica to keep on keeping us on time. Thank you so much for your attention. This is my contact information, and this is a final example of an analog meteor crater, Arizona, where we did a planetary geology course.
All right, fantastic, Shauna. Thank you so much for outlining your lessons and more about the mission of ASP. So right now we are going to go to our final presentation. It would be with Brett here. And he was going to discuss about the risk management and flight assurance of small sat mission success. All right, Brett.
Yeah, thank you so much, Jessica, and incredible job, Shauna. I believe we are right on time here, so I should have between 13 and 15 minutes to get through some of the core principles for risk management as they apply to spaceflight technology development. In this particular case, we're going to be focusing on small satellites. So go ahead and advance there. Thank you. So we have a couple, I would say, once again, core principles that in the process of focusing on risk management in this type of a setting, that we can directly apply those core concepts to making sure that we have a successful small satellite flight, and then be able to actually apply that to the continued technology development and proving grounds that are going to be associated with human spaceflight science missions, both in suborbital and orbital mission architectures. You can see those core outcomes shown here. Our focus here was originally on the university-led initiative and what it actually looks like to review risk management program-wide in that setting. But it really does come down to these 5 pillars. Managing risk in the spaceflight environment, analyzing that risk, implementing flight assurance specific to the small satellite workflow, revising risk management strategies, and some templates of which are actually included within our current I would say development timeline. And we'd also at least for our current purposes this afternoon, we're going to gain some perspective from Apollo and what that looks like for the spaceflight industry. Go ahead and advance. Thank you. So this is a cargo train wreck outside of Las Cruces, New Mexico. This was actually in August 2017. I was at a conference down at the University of New Mexico. And I was leaving the conference, and well, I had never actually seen a true actual train wreck before. I decided to snap a few photos. Luckily, no one was hurt. Like I said, this was a cargo train that was either autonomously being towed, or we were actually able to confirm later on that that there were no casualties. So this was a good thing, but it did provide some perspective as to what we're trying not to do. In short, it was a train wreck, and this is certainly what we're trying to avoid. Go ahead and advance. So let's get a practical understanding of what risk in the spaceflight environment actually looks like and what it means. NASA Administrator Jim Bridenstine has recently alluded to a critical and neglected element in project management, which is risk awareness that is managed in parallel with budget and timeline. It's this third element that is neglected in the inexperienced program. The awareness of risk must be cultivated from the beginning of a small satellite development program, and it's the culture of the development team that must include risk awareness throughout satellite development. Go ahead and advance. Excellent, thank you. So the student-led program asks, what are the standards for program-wide risk management and how do we actually implement them? They're summarized here. They include risk-informed decision-making, failure modes and effects analysis, and fault tree analysis, which includes a sub-analysis called master logic diagrams. Those are standard methods. For sponsored programs at the university level, which happen to include the Air Force Research Laboratory and NASA, risk management strategies are expected to play a significant role in satellite flight selection. This dynamic is usually not explicitly stated within the program, but it's certainly a core component for flight assurance and mission success. Go ahead and advance. So what do we actually do about it? You know, what does active risk management actually look like in this setting? Assessing and mitigating risk in the university environment needs an actionable plan. And the risk database, the FMEA, or the failure modes and effects analysis, and the fault tree analysis are all core components to this type of a flight assurance approach. However, despite these various analyses, testing is the actual benchmark for risk awareness. This is especially true since dead-on-arrival satellites have constituted around 18% of the available data on student-led CubeSat missions. Interestingly, traditional rigorous acceptance and qualification testing was not seen as efficient relative to functional testing of the flight package. Go ahead and advance. So this is a side-by-side comparison of what it looks like to analyze a system using failure modes and effects analysis and also fault tree analysis. These are complementary techniques that happen to approach a problem from different directions and are both I would say critical for industry standards. Go ahead and advance. So in the case of an actual student-led program, which is highlighted here as the exact cube satellite, I wanted to illustrate what it actually looks like to apply a fault tree analysis to this type of a system. So fault trees illustrate the connection of mission and subsystem level tiers. And as applied to exact, which is a 3-unit CubeSat developed by the University of Minnesota, this type of analysis may focus on specific risk management measures, but its true value is informing program-wide mitigation initiatives, and it represents an excellent example of a student-led initiative that ASP as an organization is continuing to foster. So fault trees are the diagrammatic connection of mission level requirements to those at the subsystem level. Within the main build phases of development, it's the utility of the fault tree to connect the existing state of developed flight hardware with mission performance requirements. In the case of exact, since it is a solar science oriented project, this set of mission objectives can be applied to the engineering unit through fault tree analysis. So the results of this analysis provide an actionable answer to the question, what is the greatest source of risk to the mission package, or where is exact most exposed? Go ahead and advance. So in a collaboration with the University of Minnesota SmallSat team, we needed to determine what those industry standards for risk analysis actually constituted, and then what it looks like to make them actionable at the university level, and to be able to do that not just across student groups, but across multiple years of development, all the way up to even 7 years of development, which is obviously more than the usual length for an undergraduate program. And we ended up breaking it into 4 key phases, which are outlined here. This strategy represents the most applicable measures for the staged development of the university-led small satellite program as applied to the sponsored design, build, and fly initiative. So as it's divided into 4 phases, each of these are driven by milestones and timeline in their various contexts. And this strategy employs specific protocols within specific contexts at specific times, both using timeline and milestone as their benchmark. Phase A is initial development and design. It's very much timeline driven with 7 subphases, once again, as we see here, which also includes not just an initial fault tree analysis, but also a cost benefit analysis. Phase B is focused on the full-scale testing of engineering and flight hardware. And we shift focus for benchmarks to milestones in this particular case. This also includes the metal levels. What I mean by that is silver versus brass versus gold level flight units, or testing units rather. Go ahead and advance. Phase C, this focuses on the validation of the satellite, not just for the launch vehicle, but also for the orbital environments as it's been designed. We essentially want to make sure that within these extreme environments that the flight package is going to be able to survive. We see here in the subphases that it includes a fault tree analysis at the flight level, a fault tree review, which will be used for on-orbit diagnostics, and also further environmental extensive testing previous to integration with the actual launch vehicle. Phase D progresses to mission operations, which are mission timeline driven. Go ahead and advance, Jessica, and thank you. So this is what we ended up with for a suggested risk management strategy. It really it summarizes what it looks like to be optimizing an active risk mitigation approach across those 4 phases. It's essentially a cheat sheet for actively managed risk. It really approaches this problem from various angles and uses the techniques as they're best applied across each one of these subphases based on its benchmark. Go ahead and advance. So we celebrated Apollo 11's landing last year. So it seems applicable not just to base this conversation in our national history and in the history of global space exploration, but also as we look ahead to next major milestones for human spaceflight. The Apollo Saturn V era assembly, integration, and testing procedure is a noteworthy comparison. In order to accommodate extremely tight schedules and high program scrutiny, program managers shifted integration and testing to an all-up approach, where fully integrated launch vehicles and their payloads, instead of their subsystems, were tested for functionality. So we can see the results of this historical approach as it was built upon dedicated and actively managed risk awareness, and how this was specifically applied to human spaceflight. Go ahead and advance. And this was the success of that effort, and we continue to celebrate it 50 years later. And as importantly, as we see with a burgeoning human spaceflight industry, we are very much confronted with developments in human spaceflight on our immediate horizon. And so we've really just covered the fundamentals of risk awareness and management for the university-led smallsat team, and we've also bridged that operational gap to be able to apply these operational principles to human spaceflight as well. at ASP, this is what we're focusing on, and we are looking forward to being able to garner input
All
from
right.
our
Thank
audience
you,
members.
Brett, for a fantastic presentation. So overall, breakout sessions, a lot was really discussed. We got to know the audience a lot more, which is always fantastic, because in these sessions, you don't really get a chance to really interact with other people who are in the session with you, and you can have some common ground and see where you guys may differ. But we talked a lot about sustainability in the space environment, robotics, and different business management, financial management, and some fun facts about some people. We might have a space bar in the future, which would be fantastic. Well, here, I hope everyone has had a fantastic, learned a lot from our session today, and would like to join us at ASP in the future. So you can join us, go on our social media. We're on Twitter at Spaceflight Pros. We're on LinkedIn at Spaceflight Professionals. Go on our website, spaceflightprofessionals.org, so O-R-G. And if you have any questions for anyone who spoke today or myself, our contact information is here on the screen here if you want to take a screenshot and ask any questions. But thank you so much for your attention. Thank you for being a stimulating audience. And we look forward to hearing from you next time. You can take it away, Chris. Thank you.
Thank you, Jessica, and the team at the Association of Spaceflight Professionals. Thank you again for joining today. This is one session in a larger series of sessions leading up to our Ascend event in November. Be sure to register for more information. Remember that everything shared today was done so under Chatham House rules. You may use the information, but you may not share the identity nor the affiliation of the speakers, nor that of any other participant. Thank you so much.